Good morning. This is week 4, our last week, where we talk about how evolution and faith often overlap. In kind of a wide variety today to wrap things up, I wanted to hit on what materialism was. And I wanted to talk about how textbooks treat the topic of evolution, what they look for proof. And the last one is actually my favorite. Help, I am a mutant. And I'll explain what that means in a minute.
Mine too.
I'm hearing a lot of feedback. It means you're not on mute. But
you guys just, everybody just mute yourselves if you're not on mute, please, so that there's no background noise, if you don't mind.
And materialism, it's an ancient philosophy. You know, the ancient Greeks had it. Today we call it eliminative materialism. It means no such thing as mind, you know, that thing, working. Only matter exists, and we're deluded to think otherwise, you know, if we think we have minds. And the starting point is really, there's no God. And there's no external mind at work doing anything. It's just matter. Matter is all that matters. And you think you have consciousness, but in reality, it's just neurons that evolve in a certain pattern with certain qualities. And you're nothing but pre-programmed by the forces of evolution, you know, to think and act in a certain way. That's all it is. You're just reacting. You know, if you think you have free will, it's just an illusion. Let me make sure I'm recording. Yes. And so people like Richard Dawkins, Francis Crick, Bill Nye, the science guy, you know, hardcore materialists. And I do respect their logic, which is, you know, first they adhere to a belief that there's no God from the outset. And so it's just matter that matters. Evolution happened. Your brain is neurons firing. There's no purpose to your existence, you know, other than atoms bunch popping around and hitting each other, and eventually life springs up. And here's where I diverge with them, though. Yet for some reason, they're concerned when God is emphasized. And they make it their life's effort to squash any vestige of belief in God. These men with no purpose, no direction, only neurons firing in a predetermined manner, they seem to have purpose. And that their purpose is to make sure everyone knows we have no purpose. And they do it with gusto. You know, they do it with anger, with, you know, repulsion at the thought that anyone could deny that they're meaningless. I find this strange. These men, you know, allegedly incapable of forming a non-pre-programmed thought, they think better than I do. I find that amazing. So presently, you know, the world of science demands only materialistic explanations for our world's existence. Yet, if there really is a God, and God designed our universe, really to exclude God as a requirement to begin to understand that universe, you know, that seems utterly non-scientific. So that's me on my high horse, my pedestal. Let's turn to key points for advancements for evolutionary theory. What happened in the past that really turned people on to evolution? There's really two key thoughts about mutation. Mutations are key to evolution, of course. That's how we get that building block cell. Fisher was fundamental. Back in the 30s, he supported a neo-Darwinian view. Basically, he said, no matter what you do in a population, we're always getting better. We're always getting more fit. Fitness means the ability to reproduce. It's always happening. You, your enemies, your competitors. And then there's people like Lynch, and I love Michael Lynch. He says, no, actually, there's areas where we see things going downhill, genetically speaking. And in fact, he says, on average, 0.2 to 2% per generation decrease in your fitness, which is your ability to reproduce. And in humans, he sees a 1% decline every generation. And I'll touch on that at the end. And if you look at a curve of what acceptance of Darwinian evolution looks like over time versus what happened over time, you know, Darwin came in, he published in 1859 his book, His Origin of Species, and you saw an increase in acceptance. But then Mendel came in with his genetics, understanding of how genetics really worked, and Darwin got kind of de-emphasized. But then something similar happened here in 1930 with Fisher, and really Fisher, Haldane, and Wright. But Fisher really, he introduced his theory, his genetical theory of natural selection. it contained his fundamental theorem of natural selection. And that was fundamental, and it really launched Darwinism into mainstream. And I'm going to explain that in a minute. A paper that came out not too long ago, the fundamental theorem of natural selection, which is Fisher's theorem, but with mutations, which is Basner and Sanford, two guys that I know. And actually, I know Dr. Basner as of yesterday. We had a Zoom meeting. He explained some of the things to me. His article, it came out not too long ago, has a lot of access. So people have looked at it a lot. It's really shaken some things up, and it registers on the high end, very, very high end of what's been downloaded and looked at. And he has a video on YouTube. Check it out. It's great. And he sent me a slide, so I stole his slides. I told him I would. And here's some of that, talking about Fisher's fundamental theorem and corollary. So Fisher basically said, if you have a population, say frogs, some are more fit than others. Some can reproduce better. So here's a scale. More fit down here, less fit is over here. And here's our 3 frogs. This one is more fit than this one. This one can reproduce better than this one. So you had this variance, this variability. And here's Fisher's theorem in a nutshell. And I get to show a differential equation as an engineer that excites me. It's the only one, don't worry. It says the rate at which you improve your fitness, get better in fitness, will be greater if you have more variance, more variation in the population. What is variance? Here's your variance from high to low. He says if you have more of that, you have frog over here, a frog over here, you have more variance, more variation. So when you begin to improve fitness, it'll go faster. Okay, done with differential equations. So this frog has babies, and there they are, and then they all have babies. And of course, here is the average fitness of these 3. This is the average. Some are better, some are worse. And of course, you have babies, you'll have an average, and basically be the same average as the population. That's the mean fitness. But selection comes in. You know, on these guys over here are less fit by definition because they're on this side of the line over here. And so they'll tend to reproduce slower or worse. And of course, over here, yeah, they're better, but still natural selection comes in. This guy, for example, was crossing the road one day and he saw a bright light and he stopped to investigate. And of course, you know how that story ends. So he's no longer available to reproduce. So since these guys are prone not to reproduce, by definition, these guys will do a better job. So what happens is your average, your mean, increases. It was here, and now it's here. And this is what Fisher says. If this is all that happens, instantaneously this will happen. That's his fundamental theorem, and it's a fact. You know, if you look at just one generation like this. But his corollary was that he said over time, if you talk about mutations and call them neutral, you'll get more variation because of mutations, and you'll have more, and thus you can increase your fitness. Now, he said they're neutral. He said that they're 50% good and 50% bad, thus neutral. That was his definition that he used. And when you do it that way, fitness always increases. And this is where evolutionists have in their mind when they think about, oh, we got complexity, it's building, great. What they're really thinking is we're always getting better. And Fisher now has given them the math to believe that you always get better. So the 3rd generation comes along, they reproduce, all these little frogs. Here's your average. Selection comes in, does its thing, and the average shifts to the right. They got more fit because there was variation within the population and the way he chose to do mutations. So this is his corollary with neutral mutations. This is what the world actually knows about, is that each generation gets better according to Fisher. This is how neo-Darwinian theory got started, you know, and it provides the fuel that over more time, this mutation process leads to species and macroevolution. You know, the bats get wings, you know, the mammals grow wings, become bats. You know, that's the fuel to fuel complex building. So, and the history of Fisher is clear. If you look at some of the histories, he said his aim was to vindicate Darwinism, to make it true, and to demonstrate its compatibility with Materialism. And he did that. which he tied the genetics to the math and to Darwin. And his book in the 30s was a rigorous mathematical framework that coupled Mendelian inheritance, genetics, and Darwin's quantitative model of natural selection. And Kunin, who's a big name in science, over 600 articles, senior NIH investigator, he says, far from damning Darwinism, genetics provided a natural, solid foundation for Darwinian evolution. And it was Fisher who tied them together. In his tomb that he wrote, his genetical theory of natural selection is second only in importance to Darwin's book. And, the hawk Dawkins, he said, you asked me who's the greatest guy other than Darwin? Well, it's Ron Fisher, no doubt about it. He gave us biology's modern central theorem. It's hands down, it's Fisher. Here's what Fisher said, though. He believed mutations are effectively 50% neutral and 50% deleterious, which means harmful. He said the big ones, really bad mutations that you die right away or you don't reproduce at all. So those are rare and they're very effective. So don't worry about those. Now, the other ones are 50-50, good, bad. That was his assumption. One problem with Fisher's view, completely wrong. The vast majority of mutations are deleterious. This is one of the most well-established principles in evolutionary genetics. Everybody knows this. And that was also from Lynch. Since most mutations, if they have any effect at all, are harmful, the overall impact of mutation must be deleterious. James Crow is a big name in population genetics. He knows this. And most people know it. Linsky, my favorite guy, last week we talked about him. He says, if you want to put a number on it, good to bad or bad to good, how about 1,000,000 to 1 is more likely? And here are other publications that say it. The last one's really got a cute title, Estimation of Spontaneous Genome-Wide Mutation Rate Parameters. Whither beneficial mutations, meaning where are the beneficial mutations? So this is how it is. Mutations are bad if they have an effect. So if you go back to look at how the opinion changed, here, Fisher built his corollary was completely wrong, and yet it propelled the thought of evolution. And that's where these two guys come in, Basner and Sanford, with a modification of that theorem with mutations. They add the mutations to it, and when you do that, what happens? Well, here's your mean fitness, and they reproduce. Yeah, one of them might become slightly better if there's a good mutation, slightly better, but for the most part, mutations are bad, and they do bad things. So overall, less fit, and everybody gets to reproduce, and the average actually now moves because they know they're bad. But you get selection, it comes in, and most of them, on average, the less fit don't do as well by definition, but some of the good guys go away too because of just things happen, and your average is here, but because of selection, and you get to pull it back a little bit, but it never goes back to positive. You always lose a little bit of fitness each generation if you count mutations correctly, and that's what this modified addition to Fisher's theorem says. You get selection, it moves back a little bit. And this is what Basner and Sanford are saying, here's what it really looks like with mutations. So Fisher and his corollary were wrong. Mutations are overwhelmingly bad, and I don't think anyone disagrees with that. The papers, that's what science says. This drives, the introduction of these mutations into a population drives fitness down. And if you look at the comments to the paper that was published, they don't dispute the math. The math is solid. Lynch basically, he commented on this, yeah, well, he shrugged his shoulders and said, yeah, we already knew this. Okay, fine. Now, I don't want to bash Fisher too hard. He was a genius. His book had a lot of other material that laid the foundation for population genetics. But I got to think, surely he knew 50 bad, 50 good wasn't true. Even though it's 1930, we're just learning about mutations and the thought of that. I think, though, his philosophy for Darwin clouded his judgment. And when he picked those conditions that led to increasing fitness, I think he knew that intentionally. And what the result was, he falsely fueled, whether he knew it or not, a revolution of Darwinian thought. Now, others, they say, well, yeah, we knew that, but Fisher really wasn't a big deal. Really, after all the quotes I just gave, his goal was to vindicate Darwin, and everybody says he built the framework that launched it. Coonan says that clearly, that his book is second to none. Dawkins, who is the mouthpiece for materialism and Darwin, he says he was number 2. So yeah, he was a big deal, absolutely. So this corollary was very wrong. So that's key to understanding how the thinking of evolution evolved. Now, I want to look at some key evolutionary theory advancements, additional ones, and also kind of look at how the textbooks see these. Because many scientific leaders, dedicated to materialism, I want to know how it's taught in high school and college. So what do you think the primary driver is? We get some inclusive review of the proof for Darwin, and we include the areas that seem to conflict with Darwin, give them equal time? Or is it more of a single-minded desire to impress that Darwin is unquestionably, correct? And if that means some points are vigorously debated or not quite as true anymore in the discussion, well, we're going to err on the side of ensuring that there's no doubt Darwin's true. A or B. I'll let you decide later which one. So kind of changing gears, let's make some organic compounds. Remember back in week 1, we talked about amino acids, right? And how you try to make one that's approaching 100 amino acids long, and you get some crazy number with 150 zeros or something. Now, in order to even start that conversation, you got to have organic molecules to come together in that primordial soup. And to do that, you got to have organic molecules, of course. And this was a real and legitimate concern for the pioneers of the theory. Like, where's the organic molecules coming from? We got the Earth cooling down, but we got no molecules. Well, we're talking about the Miller and the Urey experiment. This is a classical example. Currently, you take a deep breath, you're going to pull in 21% oxygen in our atmosphere, right? We need it. But to build organic molecules, you can't have oxygen present, and that's why some of us take antioxidants to get it out of our blood system, the free radicals. Now, in the 20s, Russian Oparin and the British guy Haldane, they proposed that maybe lightning struck through the sky in that primordial atmosphere and hit molecules and began to build these things, molecules that where no oxygen was allowed. It was a reducing environment. And those molecules then dissolve into the seas, and you got this hot, dilute soup ready to come together in the primordial ooze. Along comes Miller and Urey, 3 decades later, and they decide to test that hypothesis using the conditions proposed by these 2 guys. What they did was they took methane, ammonia, water, and hydrogen that were proposed, put it in a little container, heated the water up, brought it through here, and here's your spark right here, your lightning flashing, and it cools down, and whatever formed between these guys gets caught in this trap here, and you analyze what's in the trap. And sure enough, it produced amino acids and some of other life's basic compounds, so they were really excited, understandably so. We got the first step in the origin of life to make some molecules, amino acids, to come together. And it was, it had a great excitement in back in their day, they could find it in any textbooks, and you'll still see it today in our textbooks. This picture right here. Now, it later became known that hydrogen easily escapes into the atmosphere when it's made into space. And since 1977, an inability to retain hydrogen has become a near consensus amongst geochemists. John Cohen said in Science, many origin of life researchers now dismiss that 53 experiment because the early atmosphere looked nothing like the Muller-Urey simulation. He said there was no hydrogen available to work with, so it couldn't have been a reducing atmosphere. So no ammonia, no methane. What's left? Carbon dioxide, carbon monoxide, and water. And most agree you don't get amino acids from this. And people have tried, and have been very poor results. So we have consensus. Their atmosphere they used was not realistic. Are our kids still taught that the Muller-Urey experiment is a fact? Well, of course they are. If you look at the textbooks today, and did a quick survey, they're all still using the drawing. They all use misleading text, and I give the page number for their reasoning. And here I have some bullet points you go back and look at later. We'll look at number 1 here from Miller. He admitted that the atmosphere they used, from Miller-Urey used, was different. However, he said more recent experiments with different mixtures of gases have produced similar results. Well, it's wrong. You would have needed to use hydrogen to get those results, and hydrogen isn't allowed, and that's not mentioned. So you can go through these and look at them if you want to, but the textbooks don't hint that there's a controversy. Strange. Now, if you really want to see a guy go off on this subject, Rice University professor, he's an organic synthetic chemist, James Torr, he gives an amazing detail, the miraculous powers that must be employed from a scientific standpoint to generate organic compounds, not to mention, these coming together to create life. Check out his YouTube stuff. It's really, really good. He is an expert in his field, unquestionably. And so now we got Miller-Urey, which, again, people embraced it wholeheartedly. Now we got the molecules, and it too fueled Darwinism in our minds. It too proved to be incorrect, completely incorrect. And we already talked about antibiotic resistance. We did this last week. Go back and look at that on the YouTube videos. And because you might say, hey, Tim, 1,000,000 to 1, really? You think that's how hard, that's the bad to good? There's no way. What about, antibiotic resistance? Well, even if it's true, which is a horrible example, okay, you got 1. There's your 1 to 1,000,000. And maybe you find a couple more. The point is, science agrees they're rare. And so I won't go through all these. But the end, even if you put antibiotic in there, all you're doing is fishing out a mutant that already exists. You're doing artificial selection. And it's a bad example. And also if you're doing gene transfer to get resistance, it again is not, you're not building complexity. And of course, you don't see this one anywhere in the literature of science books, which says life just kind of showed up in full form. There wasn't some slow, gradual, increase in life in time from point 0. No, it kind of shows up, and so you won't hear a hint of this in a science book, only in passing at the best. And another great topic that's hit upon in textbooks is homology. It's another, I call it an abused item in the textbook. Now, scientists notice certain groups have similar features, yes. If you look at the wing of a bat, flipper of a porpoise, a horse's leg, a human hand, they have similar structures, and they seem to be homologous. And that's what homology is, common things, organisms, common things. The analogy is a little different. It says animals quite dissimilar but similar structures. Could be a butterfly's wing and a bat's wing. They're analogous structures. But don't panic. There's no reason for this. Pre-Darwin knew this. That was expected. They were a common designer. They reasoned. You would use a common blueprint, for creation. But enter Darwin. And he had a different idea. He says, what if homology was due to descent? One creature evolving away from another. It makes sense. One would expect many overlapping similarities to your closest evolutionary buddies, right? And then the farther away you get, these similarities begin to decrease. And Darwin said, if we suppose that an early progenitor, the archetype as it may be called of all mammals, birds, and reptiles, had limbs constructed on a existing pattern, then the similar framework of bones in the hand of a man, bat wing, porpoise leg, at once explain themselves on the theory of descent with slow and slight modifications. So Darwin listed homology as one of the facts that all descended, each within its own class or group and from common parents. And it still helped paleontologists organize fossils today based on the anatomical differences and the similarities. And then if you want to talk about more homology, the DNA should scream homology, right? If the bones are similar, then its simple reasoning says the DNA and the resultant proteins that drive the bones, it has to have some similarities too. I mean, you can't imagine the genes are different, the embryos are different, but yet the outcome is similar homology between us, a bat and a whale and a man. That doesn't make any sense. You expect some similarity and then branching and differences. So the conclusion is homology in its many different forms is at the heart of Darwinian theory, and it makes sense from a reasoning standpoint. Modern Darwinists continue to use homology as evidence for their theory. And next to the tree of life, this thing here, homology, this thing here is the second most widely shown icon in the biology books. It basically says, to be homologous, you got to have a common ancestor, and we'll get into that here in a second. And that's what it is. There are some similar features that are assumed to not have a common ancestor, right? The eye of the octopus and the human eye look very, very similar, but we don't have a common ancestor that had eyes like that. So we're not homologous. And there are many similarities to construction with that eye, yet they don't appear to have a common ancestor. In fact, there are many such theories like that, analogous features, and Morris said that convergence, is ubiquitous. He gives hundreds of examples, and convergence is like a butterfly has wings and a bat has wings, similar, but yet they had to have gotten there differently. This would seem to run counter to Darwin's belief that homology is proof. So what does the proponents of Darwin do when you have that kind of problem? Well, you redefine homology. It used to be homology is similarity due to similar structure and position, like bones in the hand and the porpoise's flipper. Now it's homology is similarity due to similar structure and position if you have a common ancestor. So now we fixed our butterfly bat and octopus human, they don't have features that are homologous anymore because they don't have a common ancestor. So this is what we call circular reasoning. New definition is homology is similarity due to common ancestor. And how this works is you say, hey, what's homology? Well, how do you define it? Well, you define it in terms of common ancestry. Well, how do you tell if you have common ancestry? Well, they'll have homologous features. And you see it goes in a circle. And Dawkins knew that, and many people realize this kind of late, it seems like. And in 2009, he said it out loud, Dawkins did. And so what was his fix for this? Oh, we'll simply rename homology and call it homeomorphic. Wow, what a fix. It's still circular reasoning no matter how you gussy it up. Here's the real problem. You got your mole cricket with his feet, and you got your mole. They got features that look very, very similar. And here's the problem. Similar features can point to having a common ancestor, and they can point to not having a common ancestor. So what does homology really tell us about the origins of life? And you can go into these textbooks and read, they will use that circular reasoning to a T. They define it, and then they say, oh, look, we got proof. But you've already defined it that way. So that's an issue. This discourse has been about, to me, it's about overplaying your hand, homology. Okay, that's why I'm going on a tangent. You get to exclude similar features that contradict the theory. Then you say the ones that are left prove your point. Well, I have to throw a flag on that one. Illegal use of circular reasoning, 5-yard penalty, repeat 4th grade. And here's a great YouTube video to go watch. You'll love it. It is hilarious. So circular reasoning aside, okay, maybe limbs we looked at earlier really do provide evidence of descent with modification. Maybe it does. And I'll introduce a term, morphology. Morphology is a branch of biology that deals with forms and structures of animals and plants. You look at, how this is shaped, that's its morphology. And that's what morphology is, looking at the outside, the embryo even, seeing how it develops. It's not the genetics. So let's take a little deeper look. Let's look at the development in the embryo. So you would expect if the limbs are homologous, right, that there would be some point in the embryo where there's a point of commonality between me and the whale, me and the bat, that there'd be some similarity, and then we branch off. Surely they share a common ancestral cartilage pattern, right? Before the bone happens in early vertebrate limb development. Again, here it is. You got these differences, but if you go back into where things first start, egg meets sperm, there's going to be some similarities. You're going to use some common architecture, and then later on in that embryo, you're going to branch off. Bat, porpoise. That's how evolution would think it would happen. And even Hinkle provided some amazing pictures of embryos. And he called these stage 1. We got from fish to salamander, and we got 4 types of mammals. And look how similar they look. It's amazing at stage 1. And then they diverge. Keep this picture in your head of how similar. So you can see how people would think, yeah, this makes perfect sense. This is what Darwin predicts. Early on, very, very similar in the embryo. Later on, we begin to separate. But unfortunately, no, this isn't true here. The cartilage patterns that dictate how this stuff happens, they correspond to the form of the adult limb from the beginning, whether it's frogs, chickens, or mice. It jumps to, oh, let's start making this limb. And there's no real buildup that they share in common. Now, why in the world do scientists therefore think? They assume similar embryo development. Well, the embryologists are a little fed up with it. And here's a quote. The idea that vertebrate limbs develop from a common ancestral pattern in the embryo has arisen because investigators have superimposed their preconceptions. They're applying evolutionary expectations by looking at the bat, the porpoise, back to the embryo. So they're not looking at empirical real evidence to say that. And we've known this for a long time. Homologous structures, arm, bat, wing, porpoise flipper, does not imply and does not equal similar developmental pathways. This has been known for over a century. Edmund Wilson, he had bad things to say about Haeckel's drawings. He said, look, it's a familiar fact that parts that closely resemble a green adult they're undoubtedly homologous. He's not questioning that, but often differ widely in their larval and embryonic origin in either mode of function or position in the embryos or both. De Beer said the same thing in 58. He says he's not seen it. In 85, it's the rule rather than the exception that if you see a homologous structure form, it's from a distinctly dissimilar initial state. If you call it homologous, don't assume you go back to the embryo and it's going to be, similar at some point. No, from the get-go, it looks different and it ends up looking similar. That's strange to these guys. So, a clear picture of homology is shown in the textbooks. You will always see this in the textbooks. I mean, look how similar our relatives are to us. Isn't that a powerful, convincing explanation? But what you're not going to be mentioned in the textbook is that these similar parts come from very dissimilar, over here, origins. That's not predicted by evolution, which leads us to another avenue to examine the theory. What about the DNA? Now, the DNA, there's the real story, right? You can talk about fossils, and that's nothing but forensic scientists looking back, trying to guess what happened. And you got your embryos, sure, but it's the DNA that drives all that stuff. If two creatures are closely related on the evolutionary tree of life, they will definitely have homologous DNA. That's got to be true in any Darwinian vision. And if you look at cytochrome C, which is a common protein that we share with many animals, you see that, absolutely. Humans, chimps. You look at the DNA sequence, it is exactly the same as a chimp. And that's what you call a conserved unit, as a conserved region of DNA. It's so important that it's conserved. We got to have it that way. And if you go back to a dog, we're very closely related, according to cytochrome C. 90% identical DNA. Moth, even less. A yeast, 50%. Very, very different. We're more distal in our relationship. It's exactly what Darwin would predict. So we should expect that same pattern no matter which gene we pick, right? Right? Yeah. In evolutionary terms, this DNA sequence has been conserved. Now let's look at cytochrome B, another very similar protein as cytochrome C, does the same thing, electron transport mechanism. What do we see? Well, if you start grouping animals by that piece of DNA, the primates are in the same club, which primates are, me, you, and monkeys. They're in the same club as whales and kitty cats. And this poor Taser here, who is another primate, he should be in here. He gets kicked out of that class. And then there's another crazy group of fish, birds, and frogs in the same group, according to looking at similarities in cytochrome B. And then sea urchins, they look like us in some respects, like they have backbones, the chordates. Like, this is totally unexpected according to Darwinian thought. Now, don't get me wrong, Darwin has plenty of explanations for this, but kind of strange. Are other people upset in science? Well, Patterson, who is a bigwig, he's, you know, the British Museum of Science, a paleontologist of, you know, amazing standing. He said, as morphologist with high hopes of molecular systematics, he was hoping that DNA would come to the rescue because the other thing was messed up. We end this survey with our hopes dampened. Congruence between molecular phylogenies, and phylogeny is the evolutionary history of an organism. We got to understand phylogeny. You know, there was a bacteria, it grew legs, it came out of the water, it became a mammal, it developed a flipper fin, and that's its phylogeny. That's its adult form evolutionary stages. How it you look back, how it evolved. That's what phylogeny is. And so you want to create connections. You want to create these molecular phylogenies that show us all linked together, like cytochrome C does. With molecular phylogenies, all generated within the last couple of decades, the situation is little better. They haven't helped. They've only clouded the situation. That is unexpected. And so I think this is Lynch, yeah, clarification of phylogenetic relationships, you know, how I'm related to a bat, to a cow, to a flea, of the major animal phyla has been an elusive problem. With analysis based on different genes like cytochrome C, cytochrome B, and even different analysis based on the same genes, yielding a diversity of potential links to all these animals. It's messed. What he's saying is, we didn't expect DNA to be so sloppy. What's going on? We are a little confused. We need secondary opinions and assumptions and theories to make this make sense. Because Darwin on its face falls flat. No. So homology is a circular argument. And when biologists try to fix it by pointing to the DNA, it only undermines their case. True, doing away with homology does not disprove Darwinism, but it does highlight some pretty lazy thinking that's common among Darwinists. It's just one more bad prediction of the theory. And if you remember, I think I said, if I didn't, I mean it, good theories are predictive. They can make some decent predictions. So what do you call it when you pick the results you like, but you ignore the ones you don't? I can't quite remember what that's called, but something to do with picking. Anyway, I won't even talk about orphan genes. That's where you have two very similar groups. One has certain genes, the other one doesn't have a hint of them. Do you think they use those for dating and showing relationships? No, they get tossed out. So don't get me started on orphan genes. Now, Haeckel deserves special attention. He really does. And I can't talk about Haeckel right now because we're running out of time. But what I want to do is show you the slides. You can go back and look at the video. Haeckel faked these drawings. Why they look so similar? Well, he faked them. It just flat out lied. And everybody knows it now. But you'll still see this in some of the textbooks, even though they're clearly a lie. And Darwin, he loved Haeckel. He based his theory a lot on those embryos, but they were wrong. And Haeckel had the biogenic law, and it turns out it was completely fraud. And Stephen Jay Gould said Haeckel exaggerated the similarities by idolization and omissions, and concluded that his drawings are characterized by inaccuracies and outright falsification. Wow. So you want to check this out. It's great story, and I won't go into it right now. And then there's pepper moths, which was the perfect example of natural selection that was told from the 50s to even to the 90s. Turns out that too has a lot of issues, simply to show natural selection, which really no one objects to. But you'll see this in the textbooks, and it's a completely staged photo because moths don't rest on the trees like was thought. So look, check that out, and it's still in the textbooks. And you can read about Jerry Coyne when he heard about the moths were fake. This is what he said, and he's one of the top guys in evolutionary thought. Coyne's reaction upon hearing the truth about the disillusionment of those moths that may become increasingly common, in biologists as they discover their icons of evolution being misrepresented. He said, "My own reaction," he wrote, "resembles the dismay attending my discovery at the age of 6 that it was my father and not Santa who brought the presents on Christmas Eve." That's how disappointed he was. That's how, and he didn't learn this until he was well into his career, that it was fake. It's crazy. So now, let me introduce to you your DNA. We all know we got ATGC, right? In our DNA, that's our 4 chemicals in our DNA, and if you string them all out, it's one giant long line. And your genome is actually exactly almost 3 million times bigger than what I have right here. It's your code. It's your code. So you got 3 billion pairs of DNA. That's a lot of DNA, right? So on average, each pair only contains about 1/3 billionth of your total DNA. So per DNA molecule, that's tiny. Here's a newsflash. Every human inherited 100-point mutations, letter mix-ups, from their parents. So the question is, we got a lot, we got a tiny. The question is this a lot? Should I worry about this, Tim? Well, this is a good news, bad news situation here. The good news is these are really minor impacts on you. I'll get to the bad news later. So let's talk about junk DNA. Around 1970, they said, yeah, we got 3 billion pairs of DNA. That's a lot. But man, there's only 1 to 2% that encode for our 20,000 proteins. That's all we need is 2%. You know what? 98% is not needed? Is it just junk? And people are like, we're like, I think it's no. We're wondering out loud, why so much junk? And Dawkins says, yeah, it's just surplus DNA trying to survive, no more, no less. It's a parasite essentially. It's hitching a free ride. And papers came out in Nature, for example, that said, yeah, it's junk. You can go look for functionality, but it's a utility, it's futile. Why bother? Crick, not a fan of this materialist, but he said, much DNA in higher organisms is little more than junk. That 98%. Since such DNA probably has no function, it would be folly in such cases to hunt obsessively for one. Forget about it, science. Don't waste your time. Thank you, Mr. Crick. And Miller, our textbook writer, in 2004, he was a big opponent of Behe's in that Dover trial. If you looked at that video, if you didn't, you need to watch it. He said, if the DNA of a human being or any other organism resembled a carefully constructed computer program with neatly arranged and logically constructed modules, each written to fulfill a specific function, the evidence of intelligent design would be overwhelming. In fact, the genome resembles nothing so much as a hodgepodge of borrowed, copied, mutated, discarded sequences and commands that have been cobbled together by millions of years of trial and error against the relentless test of survival. Yeah, nothing but junk. And he threw in a little jab. You feel that jab? He says, oh yeah, by the way, some God's got there, Christian. What kind of design is that, Christian? In 2005, another textbook writer, he piles on. He said, we can identify several patterns that confirm the historical reality of evolution. One of those patterns is that every eukaryote, that's higher animals, their genome contains numerous non-functional DNA sequences. Such patterns are inconsistent with the notion of an omnipotent creator who should be able to adhere to an optimal design provided them. Yeah, God should do it a certain way if there was a God. Another jab in your ribs there, Christian. And this philosopher in 2007, he said, if you were designing the genome of organisms, you would certainly not fill it with junk. Yet the most striking feature of the genome analysis we now have is how much apparently non-functional DNA there really is. From a Darwinian view, he says this is totally expected. No surprise here. But if you were designing it, gee. Looks like Darwin won, God 0 if you're keeping score at home. I would say, hey guys, stop it. That's piling on. I'm gonna throw a flag. Now we're at 2003. the first draft of the human genome has been published. Finally, we can see our DNA there in a book, and it's just letters, just 4 letters randomly thrown together, seemingly. There's no info on what it says and what the function is. But we got the code. And then a project called ENCODE comes along, which stands for Encyclopedia of DNA Elements. And it's a huge thing, right? In 2012, I saw a number, there were 400 researchers all over the US trying to figure out what is that other 98% doing. And this is a highly funded NIH project that's going on today. And they finally came out with something in 2007. They looked at 1% of the DNA and said, you know what? We found convincing evidence that the genome, all your 3 billion pieces of DNA, is pervasively transcribed. What's that? Remember, you have DNA, and your body comes along and makes a copy of that DNA in the terms of RNA. That's transcription. It says everything is transcribed practically, with the majority of the nucleotide subunits being present in these. It's a transcript. Not only that, although it was previously thought that only one strand, the sense strand, got transcribed, they said the evidence showed that both strands get transcribed. This is crazy. Why is our body making copies of everything in the DNA when it's just junk? Talk about a waste of energy. Darwin wouldn't predict that. But one man's junk. 2007, someone said, hey, we found something with that junk. There's some things in that junk called lines, long interdispersed nuclear elements. They actually have a job. They silence a gene that you need as a fetus, but not as an adult. So as an adult, it silences that gene. 2009, some biologists showed that RNAs cut from signs, I guess they're called signs, short interdispersed nuclear elements. They said they help control gene expression and concluded that this has refuted the historical notion that signs, a particular type of junk, were merely junk. And then in 2012, I would say all hell broke loose, because ENCODE came out and said, hey, we looked really hard, and it's not 2% good, it's not 98% junk. Actually, 80% is functional. Only 20% might be junk. That sent the world all over the edge. 30 articles got published on that time period, and they concluded that the data enabled them to assign a biochemical function for 80% of our DNA. They said we haven't looked at all the cell types yet, and so the other cell types might use that alleged junk that's left. So stay tuned. Now that sent shockwaves, especially to the evolutionists who adhere to certain dogma. For example, they said, hey, evolutionary theory demands junk, a lot of junk, and their papers written. This guy was like, look, like this, hey, we know we only have 10% or less of sequences that are similar, conserved between humans and other mammals. And we know the theory demands that only sequences that are conserved are functional. That's how natural selection works. It picks the things that you need. So they argued that unconserved sequences are not functional. So the number of human sequences that are functional has to be less than 8%. Otherwise, we have to rethink the whole theory. We need more junk because we only got 10% that we know is in common with our friends like the chicken or whatever. But others said, hey, it wasn't junk. Here's a paper that says function has been identified in many non-protein coding RNAs. Not about just the RNA. The RNA is doing something. It's not making protein. I need to be clear. That 98% not making protein, that's a 2%'s job, but it's making RNAs that do something. And he said those non-protein coding RNAs whose sequences have not been conserved, we found some function in them. That's shocking. So a lack of conservation does not mean lack of function. If you look at the sequence conservation to estimate functionality of DNA, you will underestimate functionality greatly. So Dan Guar, University of Houston, he hates the ENCODE project. He hates it, hates it, hates it. This is what he called it, an evolution-free gospel. of those encode people. He actually brought Christianity into it. He says these people are acting like creationists with their science. It's horrible. He called it their gospel. He accused the research of playing fast and loose with the term function by divorcing the genomic analysis with the evolutionary context that you have to interpret things. He said, if the human genome is indeed devoid of junk DNA, as implied by the Code Project, then a long, undirected evolution process cannot explain the human genome. In other words, he said, if genome is right, evolution is wrong. Ow, no wonder he's so upset. What's the solution to this? Let's kill the ENCODE project and stop wasting our money. Oh, he's a classic. The blinders are firmly in place because Doolittle, another huge bigwig, he's insisted that only in the light of evolution does biology make sense. So evolutionary approach takes priority. If this means labeling functional DNA as junk, so be it. And this is science. Okay, so why are they so upset? You know, I mentioned these 100-point mutations, right? That's in the back of their mind. You know, if 98% of your DNA is junk, then those 100-point mutations will predominantly hit DNA that is junk. And that's a big wasteland. It's no big deal. Junk turns into junk. It's still junk. But if 80% is functional, then those 100-point mutations will tend to be a big issue. It implies our DNA is under a serious assault. It really means our DNA is going downhill. You know, in opposite of what Fisher said, and according to what the new theory says. This implies the evolutionary model of building complex features over time would have serious issues, because after all, if Darwin lacks the capability to even hang on to what you have due to those mutations, how could it possibly improve who you are? How can you develop complex features? Hey Gar, why is this an evolution killer? He's published papers showing from an evolutionary standpoint, 80% does not work. It can't be that functional. 80% functional does not work. What he does not realize, and kind of a flip side of the same coin is, you know, if we must have, you know, plus 90% junk DNA to absorb all those mutations, that implies that every single part of the genome has an important function, a purpose, to allow the human population to endure a much larger mutational load, you know, 100 shots per generation. Then he would be wrong to say the rest of the genome has no purpose. Its purpose is to reduce the likelihood of bad mutations. That sounds like purpose to me. And I would say Darwin loses a point and God gets a point. So now the score has been changed. It also sounds like something evolution would never have predicted. Never, 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 ever. A priori. Now we're going to switch gears here and talk about Chimera and his distribution. He is a population geneticist. He's a strong evolutionary biologist. Okay, he believes in the theory. In '79, though, he published a paper that shocked geneticists, and its full impact is just now getting realized, I believe. Let me explain this graph. You got to get it. This down here is the mutation effect. If it's a good mutation, you're on this side of zero. You're positive. You're building. But if you're on this side of the neutral mutation effect, it's negative, and you're going downhill. It's a bad mutation. Now, what he said was that here's a line of the mutations on the bad side. He said most of them have very little effect. They're bad, but they're very little effect. So they're almost zero, but they're positive, but they are negative. And there's a lot of them. And as you go down this curve here, the really bad ones, you get, you know, on this side, way over here, they're really, really bad. And over here, they're really, really good. And here, they're neutral. So as you get worse mutations, luckily the frequency of those mutations is low. And that individual, you know, either dies soon or he can't reproduce. And so it doesn't matter what his problems are, he doesn't get to pass those to his kids as part of the, you know, and mutate the gene pool. So this is what this is. Here's your mutation, here's the effect it has, and here's how often it happens. And so remember those 100 mutations we got from our parents, you know? Those mutations are so minor, they have a tiny impact on you. That's the good news, bad news. Well, what do you mean good news, bad news? Well, the good news is, they have a very tiny effect. They're almost near zero. But the bad news is you can't get rid of them. Evolution, mainly through heredity and the problems with transferring genes, good genes, or getting rid of bad genes, is you can't see them. You just can't see them. They're not selectable. If you can't select a bad thing, then you can't get rid of a bad thing. Same thing with a good thing. If you can't see the good thing, you can't keep the good thing because there's no pressure trying to pull it in and keep it. And I'm going to give you an example I think will clarify that. Imagine my father has 100% lung capacity. He breathes well, but think of breathing and all the problems that can go wrong. You got to take a deep breath. You got to be able to extract the oxygen out of the air and put it into a liquid of your blood, and then distribute it. It's very complex. There's a lot of systems. Now imagine, for some reason, I get some tiny mutation, and now I only have 96% what my father had for my lung capacity. That's kind of small. I probably can tell it. My wife or my future mate who wants to have my babies, she certainly can't see it that I have this reduction in lung capacity. So she's just going to go ahead and have my babies and not realize that I have this problem. And my problem lies in the non-selection zone. Well, she's got her mutations too that I can't see. They're over here too. And so we can't select them. We simply pass our mutations to our kids, and we give them new mutations on top of that. And so that's the problem. It's bad, but you can't see it. And so my son has 96% lung capacity, and along down the line, he has a problem, and maybe it goes to 90%. And can you see 90 from 96? It's hard to see. So you can't select it, and that's the problem here. Now let's go back to that junk DNA. Remember that junk DNA? We got 100. If there are 100 mutations, and let's say only 20% of our DNA is junk. That means 80% is good. That means 80 mutations hit the good stuff. And if the components of this thought, of this junk DNA are correct, okay, fine, that's fine. Who cares? If 10% of our DNA is good stuff and 90% junk, well, that means your good stuff takes 10 hits on the good stuff. Okay? You're still mutating. And you still can't select those problems. You're not going to outbreed and pick the bad ones, and that's another part of evolutionary theory. You get rid of the bad stuff. We don't select anymore. We don't select. And plus, you can't even see those the bad ones because they're so bad. And if they are bad, they can't produce anyway, so it doesn't matter. So this is a problem. And people are beginning to realize this is how things really do work. Mutations happen, they're bad. And we don't have as much junk DNA to absorb them anymore. And so that's a problem. Okay, let's say it's 10 and not 80 hitting the good stuff. Okay, you're still going downhill just at a slower rate. Another way to look at this is, imagine here you are, born in the year 2000. Every generation is 20 years. So let's go back generation. Here we are back in the 1880s. Your grandparents, they get all the mutations from all the people before them, and they give their kids 100 new mutations. And likewise, they take all those mutations and add 100 more in. So here you go. And each year, 100 more come. And here you are with all your mutations from all your prior grandparents, and you give your kids 100 more. That's how it works. And occasionally you get a really, really bad one, or it builds up too much on certain genes, and you can't reproduce. Okay, you get kicked out. It doesn't change the fact that mutations are happening. And you might get rid of some bad ones, but even the good people who have, all they have is not as bad mutations as you, maybe. They're still going to reproduce and pass on those mutations. Okay. And did you notice Kimura's line over here on the good ones? He didn't even have a line on his original paper. This has been put here just to show. He didn't include this. I wonder why he forgot it. I wonder why. And just to remind you, advantageous mutations are known to be extremely rare. Well, that's one reason he didn't put it over here. And this curve here is actually very generous. This is shocking. Even no matter what we put here, it says, even if we do have a good mutation, nature can't see it. And therefore, it can't select for it. let's say my breathing now is 105% better than my dad. My wife can't tell a 5% difference. She ain't gonna pick me because of my 5%. And my improvement's gonna get buried in all my other problems, combined with all her mutations. And that 5% is just a little tiny blip of noise in a background of a machine gun going off, you know, destroying a target. And this makes sense. Think about the possible first step of a good mutation. You know, would a good step of a mutation, would it last? According to all the population geneticists, no, it wouldn't last. You can't select for it. So now we're wrapping up. So that was not a very good news to close out this discussion, right? You just learned how mutated your DNA is, and it's getting worse, and there's nothing you can do to stop it. Sorry about that. Yeah, not great news. This does not line up with expected Darwinian outcome. Remember what Fisher says? He said, don't worry, Mom. I'll use my Jamaican accent. Your fitness must improve. Look at my math. Wrong, Fisher. Your corollary is dead wrong. Your assumptions were horrible. This message, however, does line up with the Word of God. You were created perfect, and then we fell. And I like my use of the two words here, fail. God said things would never get better on planet Earth, didn't he? Right. Okay, current science, very recently, has given us more knowledge that this is true, more true than ever before. But there really is good news, right? God's word is absolutely true. And now, due to science, it has never been more truer than now, especially in the last 10 years. It's been an amazing discovery of science. And oh yeah, if you're an evolutionist, you have a tremendous amount of faith. And I would say to all of you, the rest of you guys, keep the faith, but please, let's be reasonable about it. Thanks a lot, guys.